Hello, everyone. Welcome to our live stream. Today, we are joined with Ryan Sigler, and we're going to be talking about overviewed RAG approaches. For those of you that are new to our live stream, we've started doing weekly live streams. There's so much to talk about in generative AI, LLMs, vector databases, retrieval augmented generation, you name it. There's so much going on. We are actually considering increasing our cadence of live streams just to keep the content flowing and keep up the pace of this super fast evolving space. So today we are going to talk about an overview of RAG approaches, or retrieval augmented generation. Now, we had a previous session where we talked about what is retrieval augmented generation. We'll do a quick little brief overview of that, but we're going to get into the core content of different approaches to RAG. Ryan's going to show that in his slides. And really where we're coming from is we see so much development and such rapid development in the generative AI space that it can be difficult to keep up with what's happening. It seems like almost every day, LlamaIndex is posting total gold on LinkedIn. If you're not seeing that, I would highly recommend following them. LangChain has a lot of great stuff that they're posting as well. There's so many different approaches to RAG. It can be difficult to keep up with all of the developments. And so what we really want to do is be strong members of the generative AI community. We're thankful that you've joined our session today. We want to be strong members of the generative AI community and help developers make sense of all the noise and all the developments that's happening out there. So to that effect, Ryan has been experimenting with different RAG approaches, and he's going to be showing that today. Now, I wouldn't be doing my job if I didn't talk a little bit about KDB AI. So I'm just, if you will give me 30 seconds, I just wanted to let you know that we do have KDB AI, our cloud-based vector database. You can sign up at kdb.ai in your browser. We have started to go on a wait list as of last week due to high demand. So I would recommend signing up as soon as possible and getting your name on that wait list. We're working to increase our capacity and increase throughput of the wait list. So, you know, I wouldn't expect you to be on the wait list for more than a week, but it's still good to get your name on that list and go ahead and sign up for KDB AI. When you sign up, you will get, you'll be prompted for a form where you enter some basic information. You'll get email verification. When you click that email verification, that's when you enter the wait list, not when you register. It's when you verify your email. And then when you're given access, you'll get an email on how you get started, and you'll be driven to this page, this admin UI, where you can manage your API keys and different API endpoints. So that's my quick plug on just who we are and why we're involved in this space. But I wanted to get started with our feature topic on an overview of RAG approaches. And one thing I wanted to mention before we get started is that you can actually ask your questions in the chat and interact with us in the chat. We do these live streams so that you can be a part of the discussion and we can help address any questions. To start with, I would love to hear from you if you're using LangChain, LlamaIndex, both, neither, just getting started. What your experience has been like. So just, you know, let us know in the chat if you're using LangChain or LlamaIndex or both. Also saw with OpenAI's Dev Day that they have a built-in RAG for OpenAI. We haven't had a chance to play with that yet, but be interested if any of you have investigated that and what your experience is. So again, go ahead and enter your questions in the chat as we go through this session. Love to keep it live and interactive. So without further ado, and one other thing I wanted to mention is that LinkedIn, where we have the majority of our viewers, tends to restart the session sometimes, and you have to refresh your page. It can be kind of an not great experience. If you go to our YouTube on KX Systems on YouTube, we're parallel live streaming there, and that tends to be a more stable stream. So if you're having issues, go to YouTube KX Systems and find us there. So without further ado, I'm going to pass it off to Ryan. And Ryan, if you want to introduce yourself and talk a little bit about these overview different RAG approaches.
Yeah, absolutely. Thanks for the introduction, Neil. And thank you all for joining. So my name is Ryan Sigler, and today I will be going over a few different RAG approaches. And the agenda is we're going to go over four sort of high-level RAG approaches that you can take. And then we'll dive into some different ways we can go in and improve these approaches. And a lot of this will be on the retrieval side. So in our RAG pipeline, as we get the data that we want, we retrieve it, the relevant data, and then pass that to our large language model. The retrieval is a big part that we're going to be focusing on today and how we can optimize that piece of the pipeline. So just a quick introduction on RAG, or Retrieval Augmented Generation. And the first thing is, like, what does this do and why are we using it? So really, what RAG does is it allows us to use the power of LLM on our own data. So large language models, they've been trained on tons of data, but they haven't been trained on like our internal enterprise data or anything that's been newly released, like new technical articles or documentation or even the news or the weather, things like that. So it's not going to be able to answer questions on this data that it hasn't seen. So RAG is a method where we can introduce this data and we'll retrieve the relevant data and then pass that to the large language model for it to be able to answer questions on. So in the RAG pipeline, there's really two kind of sides to this. And like I said, the first one is the retrieval side. So that's where we extract relevant data from, like, for example, enterprise data or new news articles, whatever, and we extract that. And when we do that, then the next step is generation, and we pass that extracted relevant information to the LLM, where it can use that to answer questions about that data. So with this pipeline, we've allowed the large language model to answer questions about data that it hasn't been trained on and data that it hasn't seen. The other great part about this is number one, of course, it can answer these questions, but number two, it's going to increase the accuracy of the responses of our LLM because it's going to reduce the risk of it just hallucinating an answer because it doesn't know. So those are some of the big upsides of using Retrieval Augmented Generation. So there's a few tools that are commonly used with RAG, and Neil mentioned a couple of them here. So LangChain is one of them. And just a quick overview here for those who don't know. So LangChain is an open source framework, and it is built to help developers create applications that are powered by large language models. So there's all sorts of different things that you can do with this, like loading and processing, chunking your data, indexing your data, agents and tools, which help with decision making and next steps within your RAG pipeline, and then LLM chains and retrievers. So there's a ton of different use cases that LangChain sort of covers, but it's really kind of meant for these broad use cases, and there's many different things you can do. It's a little bit more flexible than a different tool called LlamaIndex. And LlamaIndex is similar in a way. It's another open source framework, but I would say it's maybe more focused on a few key areas of working with LLMs and building applications for LLMs. So it's really more focused on the data parsing and indexing and retrieval pieces of working with data and building, for example, a RAG pipeline. So we'll see a couple examples later on in this presentation of where you might use LangChain and where you might use LlamaIndex. And the nice thing is you can actually use both of these at the same time too if you wanted to. So what, and one more thing with LlamaIndex, because it's more focused on the indexing and the retrieval piece of things, it's likely going to be a little bit more efficient and quicker for working with these specific use cases. And then finally, KDB AI, it's our vector database, really high speed. It offers multiple methods of similarity search and different ways to index your data. But it's also got the capability for time-based filtering capabilities. So that's another thing I'll be talking about later in the presentation. All right, so let's get started here, getting into some of the different RAG approaches. And the first one I'm going to talk about is naive RAG. And there's actually a notebook in KDB.ai if you wanted to go look through that, which actually builds a whole code pipeline on how you can build this yourself using KDB.ai and LangChain. But the general idea of this is we want to take our data and we want our large language model to be able to answer questions about it. So how this works is when we ingest our data, we'll actually chunk that up into smaller pieces. And the reason we do this is because a large language model has a limited context window. And that means we can only pass in a certain number of tokens or a certain amount of data into this large language model. And it's likely that your whole data set probably isn't going to fit within that context window. So we need to chunk it up into smaller pieces. And in a couple of weeks, I'm going to be doing a deep dive talk on this chunking step, actually. So there's several different methods to chunk and how you pick your chunk size. And you can chunk based on the structure of the document and all sorts of cool stuff. So check that out if you're interested. That'll be coming in a couple of weeks. But after we've chunked our data, then we need to embed it. So all of this means is that we're taking our raw text, our raw data, and we are running it through an AI embedding model that will turn it into a numeric representation of the original text. And the representation holds a few different things. It holds the meaning of the word itself, but it also will show the context of how that word relates to other words within that chunk. And that's a pretty powerful thing because you can actually get some semantic meaning from these embeddings. Now, once we've embedded all of our chunks, we can store it in a vector database or a vector store like KDB.ai. And at this point in the naive retrieval process, we have our data chunked, embedded, and stored in the vector store. And this gives us some unique capabilities. So when a user asks a question, say about our data set, that question is going to be embedded the same way that our chunks were embedded. And when it's embedded, we have it in that vector embedding format, and we can do a semantic similarity search between our user prompt and between our vector store. And so what that will do, there's a few different ways we can do it. We can use example search method like cosine similarity or dot product or Euclidean distance. And with this, we can find what are the most similar vectors in our vector database to our user prompt. And then we can extract those, or in other words, retrieve them and extract the most related chunks of data from our vector store. So this is the first step in the RAG process. This is the retrieval. So we've just retrieved that relevant documentation, those relevant chunks from our vector store. Now, this is the point where we augment or we pass this information into our large language model. We pass the query in as well. And then the large language model will be able to answer questions based on that context that we just gave it, and we respond to the user. So this is a naive approach. And the reason it's called naive is because when the user prompts, it's always passing this user prompt to the vector store to do a semantic similarity search. But the thing is, what if the user is not asking about the data set that's in there? So for example, if we had a data set about a bunch of data science concepts, a user prompt asking about the weather is likely going to return bad results. So it doesn't make a whole lot of sense to use this like in a production standpoint. But if you wanted to just experiment with this and really get your head wrapped around how all these different elements work together, it's a really good way to get started.
Yeah, and I also thought that using naive RAG actually might be useful in the cases that you do want to limit to a certain knowledge set. So if you're making like a support chatbot and you don't want it to go outside the scope of the documents and context that you're giving it, that might be actually useful to limit it to the knowledge that you've given it. I don't know. What do you think about that, Ryan?
Yeah, absolutely. I think that's something you could do, and to maybe help with that, you could actually have a bit of post-processing after your similarity search to say, we need it to be at least some level of similar to it. So if it's completely, it may be the most similar that we find, but if it's really not that similar, there's a limit we can put on that. So then we wouldn't even return anything if it's not similar enough. So that would be one example of how we could do that.
Thanks.
So how could we maybe think about solving that problem? And this brings us to our next method, and that's using agents to assist this RAG process. So we see at the top, it's a similar process. We're ingesting, chunking, and embedding our data, storing it in KDB AI, our vector database. But the main difference here is we're adding an agent. And you can think about an agent as sort of like a wrapper around your large language model. And what it does is it can make decisions on what should be the next step based on our user query. And it does this by actually making a call to a large language model to help it decide. But we get a user query in, and the agent will decipher that query using a large language model call and decide what are the next steps we need to take. Now, an agent has access to tools, and as a developer, we can give it access to tools. And a tool is just really kind of like a function that will do something that we wanted to do. So, for example, let's say our user asks a mathematics question. The agent would realize, okay, the user's asking a question about math. What we should do is pass it to a calculator tool. We don't need to pass it through our RAG pipeline. We can just pass it straight to the calculator tool. The calculator will do its calculation, send it back, and we can return that to the user. And there's many different types of tools. Like you could have a web search tool, for example. So I need to find some information off of Google, or I need to look up a Wikipedia article. So agents have access to many different types of tools. And if you're interested, both LlamaIndex and LangChain have a good amount of documentation on this. So one of the things about this is if you did want to go through your RAG pipeline, you can create a tool to send that query through the RAG pipeline as well. So you have kind of ultimate flexibility here. The thing is, you are doing an initial large language model call up front. So, it's a little bit more overhead. Obviously, another call is going to cost a little bit more money potentially, and then take a little an extra amount of time as well. So just keep that in mind as you're working potentially with agents. And there will be an article release actually in the next few weeks on several different topics, but agents will be one of those topics. And then maybe about a month, I'll be doing a deep dive talk on agents specifically. So stay tuned for that.
Hey, Ryan, I know we are moving along in the different RAG approaches, but I just we do have a bunch of questions coming in. Okay. I wanted to bring some up. So Mondi was asking that you were talking about RAG reducing the risk of hallucinations and having quantified that reduction in risk. So one thing that I was actually reading about this morning was an OpenAI cookbook that was talking about fine tuning. And let me see if I can share that screen. So share screen window. Yeah, here it is. Some fine tuning can be employed as well as RAG. And what you can do is they use the Squad data set, which is a question answering data set from Wikipedia articles. And they ask it questions where they have an expected answer, and they have they have an approach to have the model, the LLM, say, "Oh, hey, I don't know the answer to that." And so if you do just the baseline, you can see that it answers correctly 83% of the questions, but it answers incorrectly 17% of the questions and doesn't skip anything. Some fine tuning can be employed where you can actually have it would answer less questions correctly, but it would skip more questions and have less incorrect questions. So it's kind of the cost of your false positives there. And if you'd rather have it skip a question. So that is something that you can find on the OpenAI cookbook. You can find this on fine tuning, and they use Retrieval Augmented Generation with this. So that's a great article. And then I don't know if you had anything you want to contribute on reducing hallucinations with RAG, Ryan, on that.
Yeah, I mean, I think it does sort of depend on the use case and the data that you're introducing to it. I think there's a few hyper parameters that you can adjust that would have a large impact on that. Maybe one obvious one is the chunk sizes that you're setting and the method that you're using to retrieve those chunks. So that's something that I think would have a pretty big effect on it. And also the top, if you're returning like a top K number of chunks, how many are you returning? So I think all of those things would have a pretty major impact on the hallucination piece of it.
Great. And we had a question from a LinkedIn user. If there was only one similarity match returned at a time, this just depends on how you have your query set up with your vector database. So it will give you, if you're using Euclidean distance, it will give you the distance metrics for similarity, the distance score for each of those chunks to your query vector. And you can choose if you want to only use the most related, the most similar match, or if you want to use multiple matches, which you likely want to do in RAG. All right, so we got some more questions coming in, but I think we'll come back to them throughout the session. Let's maybe proceed with the Guardrails RAG.
All right, sounds good. Thanks. Thanks for the questions, everyone. Keep them coming. So like I said, the agents, there's a bit of extra overhead there because you are adding this additional large language model call right at the beginning of the process. But one way that we could potentially solve for that problem is using a package called Guardrails. And this is a package from NVIDIA NeMo. So you can check out the documentation on their site. But really what this does is it sort of meshes like a traditional chatbot dialogue building method with RAG and LLMs. And it starts to answer the question, is our prompt similar to some specific defined topics that we will actually create? So if you look in this box here, this is really the focus of this slide. We can almost consider this to be similar to an agent, because what we're doing here is helping our pipeline to make a decision on which direction should we take. Should we go through the RAG pipeline? Should we just send a query directly to the large language model? Or should we potentially just have a preset response? So let's just take an example. Let's say we don't want our bot that we're creating to answer questions about politics or about finance, for example. So we can define these as guardrails with this application. And what happens is these guardrails will be stored in a vector space. So you're almost doing like a mini similarity search with your user query to that vector space where these defined guardrails are held. So if a user asks a question about politics, it will compare this to the defined guardrails that we have and see, yes, this is about politics. And then we can set a preset answer to send directly to the user. So the big benefit here is we have the flexibility to create specific topics that we want to control the conversational flow with. So then we can send that, hey, we're not going to talk about politics, or hey, this is actually related to our data, so we're going to kick off the RAG pipeline. So it's a decision-making process, really. But the nice thing is it doesn't take a call to the LLM to do it. You're just doing a very fast similarity search in a vector space to prove this out. So this is just an example configuration file for this, just to show you, how you might set something like this up. But you would, define whatever model you wanted to. And then here we can define our guardrails, our limits. So we define when will a user ask about finance. You give it some examples of what that might look like. And then you give that, okay, well, we don't want our bot to send this to the large language model. We want to send a direct response to our user about this. So you can set that direct response. I'm a bot, I don't talk about finances. And then you define that flow. So the user asks about finance, the bot will send this answer about finance. Then you could potentially take a next step after that. But what about the case where we have our data set about data science and the user does ask a question about data science? So you can define that flow here too. So, here's some examples about data science. And if they ask a question about data science, we can go ahead and execute this RAG flow. So we can write a function that will execute the retrieval piece of this. So it'll go get our most relevant chunks of data from our vector store, and then the generation piece where it'll send it up to the LLM to get a response. So this is a lighter way to kind of do what an agent does. But in the same token, there is some manual prep work that you have to do to define those topics that you want to steer your conversation for. So give it a take, but I think it was a pretty interesting method to take a dive into. Okay, so the final sort of high-level architecture we'll look at for RAG is knowledge graph aided RAG. And knowledge graphs, they've become quite popular in the last few years. And it's a type of database where instead of rows and columns that you're storing data in, you're storing data in nodes and edges or nodes and relationships. So it's a really good type of database for storing data that is really focused on relationships between data points. So like a good use case would be fraud detection at a bank, potentially. But if you have a knowledge graph, you can still do RAG on that as well. And it's a similar way where instead of chunking up documentations, you just take your different nodes in your knowledge graph and embed those nodes, store those in our vector database, same type of thing, use your queries, we embed that query. We can do a semantic search, similarity search between our query and the vector database. And then what we'll get out, what we'll retrieve is relevant nodes, just like we would retrieve relevant chunks. But the nice thing about when we have a knowledge graph is that these relevant nodes, they're part of the graph. So what we can do is we can actually branch out. We could traverse from the nodes that were returned to get some additional nodes around it and their metadata as well. So all of a sudden, not only do we have our relevant nodes, but we can bring in nodes all around these relevant nodes to add extra context to give to our large language model to answer the user query. So this is one way that we can sort of look at using RAG with the knowledge graph. One thing I will say too is that there's some other architectures you could kind of think about with this, and one of them is like asking a large language model to write graph queries for you. So you can have a large language model that specializes in transcribing natural language into graph queries. So you could use a large language model to write these graph queries to search your knowledge graph as well. So that's another way you could use a knowledge graph in this instance alongside a large language model. All right, so those are the high level approaches that we talked about today. But now we're going to get into some of the ways that we can improve these approaches. And specifically, we're going to be getting into different methods of retrieval and how we can improve retrieval.
I'd like to take a pause here also because we just have a lot of questions coming through, and I want to make sure we get to some of them. If we don't get to your question in this session, we will answer them in the comment section after the session. But I anticipate there'll be a lot of questions on improvements and optimizations for those of you that are already knee deep in RAG. I had an interesting question from Brian Gallagher, and he was asking, do you have ideas on what the impact of new GPT-4 128K context sizes will be on RAG best practices? I don't know if you saw that.
Yeah.
It's about the equivalent of a 300-page book that you can now put into the context window. And I just wanted to add my quick thoughts on it is that these context windows are getting longer. Fine tuning is getting cheaper and faster, but it was really reinforcing to me that RAG is going to be here for a while because OpenAI built in RAG into their platform, and they wouldn't have done that if they didn't see that as a future state of a continued state of how you facilitate these LLMs and facilitate generative AI. But in terms of the context sizes and the chunking sizes, I know you have more content that you're going to do specifically focused on chunking in a couple of weeks, but maybe you can give us a preview of what you think the impact of a larger context window will be on RAG best practices.
Yeah, it's a really good question. So, I think in general, it's a good thing, right? You can put more data and provide more context to your large language model. But like Neil said, at a certain point, the more information that you're passing in, the large language model is not going to be able to accurately retrieve all that information like it would with a smaller context. So that's why you have like the chunking capabilities of a RAG pipeline that still seems very important. And of course, OpenAI seems to be going down that path as well. But a little bit more specifically, what I've seen is that when you're passing in a very large context, the large language model will be able to get information from the beginning of that context and the end of the context, but in the middle, it's going to have some problems with that. So that's just what I've seen. So yeah, I think, it's a good thing, but it's just something we need to be wary of. A larger context isn't always better.
Great. And Ivan was asking about NoSQL databases and if they could be used as an alternative vector databases. My take on this is NoSQL databases are very powerful, especially document databases. The key difference, though, is going to be in the embedding model and the similarity search. So with the embedding model, you are actually able to take this structured and unstructured data and create a high dimensional representation of that complex data that you can't do with a NoSQL database, that you have to manually tag that data and manually log that data. So you're using the power of deep learning here in transformer architecture to capture the importance of your unstructured data. And then that similarity search is going to give you an approximate match. So rather than having to do exact matches like you would do with other traditional databases, the approximate match is going to surface better context faster. I don't know if you have anything you want to add to that, Ryan.
No, I think that covers it pretty well.
Great. Well, y'all keep the questions coming. We're going to keep getting to the questions, but let's go ahead and jump back to the presentation on optimizing RAG and RAG improvements and optimizations.
Okay, sounds good. All right. So the first optimization method or retrieval method that we're going to look at is called structured retrieval. And really, the way I sort of think about this is it's using metadata to assist retrieval. And let's just take an example. You have maybe a database that has information about movies on it, but we can attach some metadata to each of these different movie entries to give us a little bit of extra information. So like we might have genre or year, the director, the rating of the movie, and then a description and a type for each of these. And with these metadata fields, we're tagging those embedded vectors with this additional data. And this gives us some additional capability to do some pre-filtering before we go out and do an exhaustive similarity search on our entire vector database. So let's just, for example, we are looking for a movie with a rating that's greater than 8.5. Well, we can do a filter to filter out all of the embeddings that have the metadata field of a rating that's greater than 8.5. And then we can do our similarity search with whatever query we want on only those movies. So this would increase the efficiency of our retrieval process. But there's a little bit more of an advanced way to do this that I think is pretty cool. And it's using a large language model to do this sort of in an automatic way. And how you do this is you give the large language model the metadata schema that you have. So you would give it a file like this, and it's able to learn what that schema is. And then you can use the large language model to tag incoming queries with that metadata. So for example, the query might be, I want to watch a movie rated higher than 8.5. Well, in this case, the large language model is going to be able to tag this query with that rating, and then it's going to be able to do that filtering automatically. So it's a really interesting and powerful way that you can use to use metadata, all that extra data that we have that we might not be embedding in the description, to do some pre-filtering and make our similarity search go much faster. And one good example of this is time-based retrieval. And this is one of the specialties of KDB AI. But what we can do is tag dates and times as metadata on our embeddings. And when we do this, there's different ways we could do it. We could put when was this article published? When was this last updated? You could use different time series data and tag it with all that date time information. But this will allow us to do a similarity search on our vector database with that time range filter on it. So we want to retrieve embeddings within a specific time frame, or we want to retrieve embeddings within the last 7 days, something like that. So this is a really powerful way that I've seen that you can get, the most recent embeddings, for example. And I think this is pretty interesting because you could even use this to like weight the importance of different embeddings. So if I want to give a little bit of a higher weight to embeddings that are more recent, then that's one way we could do this with. So time-based retrieval, using metadata to do some pre-filtering before we're doing our vector search on our vector database. Oh yeah, and also you can do auto retrieval with this as well. So same type of thing, train or give the LLM our metadata schema with that time metadata in there, and then it will be able to infer that time frame depending on what the user's query is. Okay, so that is the structured retrieval, and then here's a sort of another way to do retrieval, and I think they really sort of solve for a similar problem because with metadata, you're tagging your embeddings with a specific metadata tag. Well, in this case, you're basically giving an agent to each document separately. So you're handling them separately. And why would we want to do this? So let's say we have similar documents that we want to do, a vector search on, and we want to do a RAG pipeline on. It wouldn't make a whole lot of sense to chunk up these documents and put them together in the same vector database. So like if you had two like financial documents from two different companies, they're really going to be quite similar. So doing that, putting them in the same vector database is probably going to cause some confusion with that similarity search, and then you're not going to get the most relevant data. So this is a method where we actually handle the documents separately. And we'll work from back to front to try to explain this, but this is an example where we have two different documents that are similar, but we could have multiple retrievers for each document. So let's say we want to be able to answer questions with a vector database about document number one, and we also want to store a summary about document number one, just in a list. This is two different methods of retrieval, and we can use them both really at the same time. And we'll do the same thing for each document. So each document will have its vector space. Each document might have a summary. And then we have an agent attached to those. So what the agent does is like before, same type of thing. It can decide next steps based on a user query. So if the user was asking like a specific technical question about a vector or about the document, it would know, okay, I need to send this to the vector search. Whereas it's more of a high level question. It just really is looking for a summary. We can just send it to the summary retriever. So the document agent will decide the next steps. The next part of this is we would put an index on front. And this is just a high level description of what each document is, maybe a title, a sentence or two of what this document is, explaining it. And then we come back to the recursive retriever. So what happens here is you get a user query. It's referencing one of these documents, and then the recursive retriever will evaluate that and then send it off on the right path depending on that user query. So if a user is asking a technical question about document number one, it'll send it through this pipeline. It'll hit this agent. The agent will say, okay, well, this is a technical question. We're going to go to vector Q&A, get our most relevant embeddings, and then those will be retrieved and sent through the rest of the RAG process. So this is a recursive retrieval engine, and this is from LlamaIndex. If you're interested in learning more about this, there's several different examples on their documentation about how you can use this. Document agents is just one of these examples. There's other ways we can look at using recursive retrieval as well. And one way is dealing with hierarchical data. So if you had large documents that you wanted to chunk up, you could chunk those into larger chunks, and then you could even chunk those chunks into smaller and smaller chunks. So you have a hierarchy of chunks at this point, and you could use a recursive retriever to sort of evaluate that and then choose the right chunks to retrieve. So there's a few different use cases that you can use the recursive retriever for.
What might be some best practices for when you would use that chunking of chunks, that hierarchy of chunk?
Yeah, so if you have like very large documentation that would not fit into the context window, you might want to do that. And you would want to do the hierarchical because there's some different advantages to different sizes of chunks. So if you had a larger chunk, it's going to have a lot more context in it. But when you have a smaller chunk, you're going to be able to do much more accurate similarity search against it because it's a smaller chunk. There's less information there, so it's more granular. So when you're doing that similarity search, it's going to be more accurate than searching over a larger chunk. So by having some different sizes of the chunks, you can sort of adjust for how you want to do that similarity search, and then hopefully that would help you to increase the relevance of your retrieved data. And that's actually something we'll be talking about just in a few minutes. All right, so the next one is re-ranking. So this is another method for improving how we are retrieving chunks. And how this works is we have the typical way we chunk and embed and store in our vector database. But when we're doing this embedding, and we're doing a similarity search on those embeddings. The thing about it is really it's sort of like a compression where you're taking your raw data and then transforming it into embedded vector of numbers. So it's possible you might lose a little bit of information while doing that. But secondly, when you're doing the similarity search, it's doing a similarity search in a vector space, just looking at the distance between vectors or how similar the angles are between vectors, depending on the type of similarity search you use. So you're going to get relevant chunks out of this when you're retrieving your chunks, but it's not necessarily a guarantee. Like, for example, if we wanted to retrieve the top 3 chunks, it's not necessarily a guarantee that the vector database will give us the absolute best top 3 chunks with a similarity search. A re-ranker will help to guarantee that we can get the best possible chunks, related chunks. So a re-ranker is a way to do similarity search, but it's using a transformer or a deep learning model. So it's a little bit heavier of a process. It's going to take a little bit more time than a very fast vector search, but it's going to give us a much better similarity score because it's really taking into account that context between the user prompt and then any relevant chunks. So what we would do is use the fast vector search for our advantage. We would pull out maybe a larger subset of relevant chunks than just the top 3, maybe the top 25. It's just an example. It all would depend on use case. But you're going to pull out a larger amount of relevant chunks to try to make sure we capture every possible relevant chunk in those top 25. And then we use a re-ranker to compare these top 25 to our user search and put out the top 3 from there. So the goal is to provide the absolute top most relevant chunks using the re-ranker. And this sort of brings up the obvious question of why wouldn't we just pass all of our data into the re-ranker? I mean, it's a more accurate similarity search. The reason is it's more expensive. It's going to take longer. It's not really realistic to pass our entire data set into a re-ranker. Using a vector search here is going to be much faster, and it's still going to yield good results, but this is just that extra added guarantee that we're going to get those top relevant chunks. And then these would be passed on through the generation process. All right, so the next topic here is called chunk decoupling. And this is the concept of treating the generation piece and the retrieval piece differently, because they're really 2 different steps. So we can treat them differently. And here's a couple ways we can do this. So one way is called document summary. And this is where we take our documents that we're ingesting and we do a summarization on those documents. And I'm going to be doing a deep dive on summarizations in the chunking presentation in a few weeks. But we can summarize these documents. So the summaries obviously will be much smaller than the document themselves. We'll embed those summaries and then store those summaries in our vector database. But what we can do is we can link those summaries to the original raw document. So then when we do our similarity search, we will retrieve the most relevant summaries. But instead of passing the summaries to the LLM, we're going to pass the original raw document to the LLM in its entirety. So this will provide a lot of context for the LLM to answer questions. So it's treating them differently, right? You're using summarizations for the retriever, and then you're passing the entire document into the LLM for generation. The next method is called sentence text windows. And this is where you would chunk your documents at a sentence level, so very small and granular chunks. And then you embed those sentences, store them in your vector database. And then similarity search, the relevant sentences would be retrieved. So this is great, like I was saying before, because when you're dealing with small chunks, you're going to have a more granular information in those chunks, and the similarity search is going to be highly accurate. But if you were to provide only the sentences as context for generation for the LLM, it's really not the best solution, because you're just providing so little context within the sentence itself. So the method is to take that sentence and then pass a larger window of text surrounding that sentence to the large language model instead of just the sentence itself. So this is a really good way to get a highly accurate retrieval, and then also pass in a lot of context to the LLM for generation. And then one other method here to talk about is called parent document retriever. And I believe both LangChain and LlamaIndex have versions of this. But this is sort of similar to the document summary, but we're not using summarizations here. We're just chunking. And we're chunking up our parent documents. We're embedding those chunks, storing them in the vector database. We retrieve the relevant chunks during our similarity search. But those chunks will be linked back to the parent document. So instead of just passing the chunk in, we'll be passing the entire document into the LLM for added context. Now, this is where you can start getting into the hierarchical chunking, where you're taking, a large parent document, chunking it into, maybe say page size chunks, and then chunking that into paragraph size chunks, and then chunking those chunks into sentence size chunks. So we can have many different, basically a hierarchical schema of how we're chunking this. And then we can use the same method here, where we would really only embed the leaf nodes, the chunks, the smallest chunks at the bottom. And then depending, we can pass on either a parent chunk or the parent document, depending on what we wanted to do with that. So there's a bit of flexibility with how we're handling it. But again, this is the idea of handling retrieval kind of in a smaller way, and then passing larger context into the large language model. So these methods should help increase the relevance of your retrieved chunks, and also give as much context as possible to your large language model.
So related to chunking, there's a question from Daniel. He actually posted this about 15 minutes ago, but he was asking, when creating embeddings from documents of different size text lengths with use cases that need different length responses, is there a best practice on chunking size, or is that more of I'm wondering, is that more of a prompt engineering facet, where you ask it to be more expressive or be concise, if those are things. And I know there's a lot to talk about with chunking, so we can, we have that other session for it, but for now, maybe give a preview of what you think about it.
Yeah, absolutely. No, I would say that problem would probably be more on the prompt engineering side, because really, when you're passing these chunks of data to the LLM, it's just using that to reference so it can answer the questions. It's not really deciding how long of a response it's going to give based on that data that's being augmented with for generation. So I would say probably more focused on the prompt engineering.
That's what I was thinking as well. And Chamberlain Tejaswi was asking, she's using naive RAG, but sometimes she's getting questions that are outside the context provided. And so she wanted to restrict the model strictly to the documents provided, and wanted to know if you had any advice on how to achieve this. I'm not sure if this is where Guardrails comes in to really focus the RAG application towards the knowledge provided.
Right. Yeah, I would think that's something to look into, would be the guardrails if you really want to have it focused on that kind of conversational track that would only be related to your data set. The other thing, like I mentioned earlier, is you could do a bit of post-processing where based on the similarity scores you're getting on the vectors, you would need to have a similarity score above a certain threshold before that would be returned as context for the LLM. So if you were asking questions that aren't really related to the data, you wouldn't be getting anything back because you wouldn't be retrieving anything because it wouldn't be over that threshold of relevance.
Right. And then I'm going to try to combine two questions into one here. We have Mashindra Nale, and he was asking, he is looking to make API calls to his backend instead of to text retrieval. And he wants to get the contextual data from that backend. I'm assuming that backend is a database that he's trying to retrieve from. And then Raul on YouTube was asking if HTML can be used as a metadata for retrieval. So the reason I think these are somewhat related is we're talking about HTML and SQL and backends different than text data. My understanding is that you have different retrievers for backend systems that you can use, and then HTML can absolutely be used as metadata as well. Any data can be used as metadata.
Yeah, absolutely. And LangChain and LlamaIndex, they both have a ton of different data ingesters. So kind of whatever file types you're working with, and you should be able to ingest that into this RAG pipeline, no problem.
Great. I'm just being conscious of time here. So I know we've gone over where we typically are at around 30 to 40 minutes, but I know you have some more content. So maybe we can get through the rest of the last couple. I think you're towards the end of your slide.
Yeah, I just got one more to go. So
one more slide to go, and then we can answer any last questions and wrap up the session.
All right, sounds good. Let's do it. All right, so the last slide is sort of looking up front in this process to when the user is writing a query. And it turns out that users don't always write the best queries. So what we can do is use a special retriever, and LangChain has this option, and LlamaIndex might as well, but I know the LangChain one, where the LLM will actually generate similar queries based on the user's input query. So it might kind of restructure how the question's asked or reword that question. And what this will do is give several different options for the user's query, and all of those will be used in the similarity search with our vector database. So the idea is hopefully with a few different versions of these queries, we would be able to get better retrieved chunks of data from our vector database. So the LangChain one is the multi-query retriever. There's just a quick blip of code here. You can set this up. Basically, you set up your retriever, and then you pass in the query, like what are the key capabilities of data science tool pandas. And then using this, this would be able to generate multiple queries that are similar to this, but slightly different to help with retrieval. So that's the last slide there. Really appreciate everybody joining. And I just want to say, there's these are just a few of the different options that are out there to improve your RAG pipeline. Some of the ones that I found most interesting myself. But there's many more out there too to explore. So if you found this interesting, I highly recommend looking through some of the LangChain and LlamaIndex documentation. There's several other types of retrievers out there that you can use to improve your retrieval. And so yeah, that's what I got. Appreciate everybody. Thank you.
Yeah, and I think what we're seeking to do is trying to distill all the information that's out there. And even as we're distilling this, I mean, I feel like my brain's exploding with everything I've just learned with all these different RAG approaches. There's just so much going on. But I think your presentation did a good job making that digestible for me and helping me understand some of the nuances. So I appreciate that. Hoping our audience feels the same. There were a couple questions, but I think it's actually a good chance to talk about what we're going to do next week. So Madi was asking if there's any guarantees that your RAG will retrieve the most relevant context. And he was also asking if it's arbitrary to the risk of not getting the correct context, how you set the threshold for relevance. So this was a question that we are seeing very the question we had internally, and we're seeing also surfaces, how do I know that my RAG results are even the most accurate results or the best accurate results, right? Because it is in some level subjective. Yes, you get a similarity score that's quantifiable, but is that similarity score, is my embedding model correct? Is that similarity score representative of what I was expecting to see in my results? So we have a presentation that we're going to do on when this is a huge topic. So we have a presentation that we're going to do on, let me share my screen here. Yes. On evaluating RAG performance. Oops, let me get this out of the way. Evaluating RAG performance. So Michaela Woods, one of our senior technical evangelists, is going to do a session on looking at Rogue, Blue, RAGAS. There's different actual frameworks for evaluating how your RAG's performing. And we're doing these sessions every Wednesday at 11:30 a.m. Eastern. That's 4:30 p.m. In the UK. So same time next week, we will do this session. You can sign up for that on LinkedIn. You go to our LinkedIn page, go to follow, you go to our events, you'll see us in the events. So recommend signing up for that, where we're going to go take this a step further. And then the following week, let me just show you what we have planning coming down. So the following week is Thanksgiving in the US. We're going to take that week off for a live presentation, but November 29th, we'll talk about chunking methods. And if you have questions, you don't want to wait 2 weeks for these chunking methods questions, go ahead and follow me, follow Ryan on LinkedIn, message us your questions. Yeah. Happy to help you. We did start a KDB AI subreddit. I just started it this week, so that's a place where you can ask questions specifically to KDB AI or on RAG, or ask on the LangChain and LlamaIndex subreddits. Those are good places, and we're going to expand our own Slack community to allow people to ask questions there too. So various ways you can get a hold of us, but we are going to do another live session on November 29th on chunking methods. Then we're going to move on to agents with LLMs, and then we'll talk about some specific KDB AI stuff with Amazon Bedrock. These sessions are recorded, so that just came up. So you can find them on LinkedIn, but I would recommend watching them on YouTube. You're going to get a little bit higher quality. So follow us on KX Systems on YouTube, and you can watch these live streams in perpetuity there. Did I say that right? But they'll be available for you to watch. Thanks for the questions. We're going to go ahead and answer the questions after the session in the comments, and we hope to see you all next time. Thanks again, Ryan, for the great presentation.
Thank you.
All have a good week and weekend ahead. And yeah, have a good week. Thanks. Bye.